This question is asked in GATE 2023 of electrical. This is from digital subjects and related to microprocessor or microcontroller topic. General student, this is not in the course, but anyway the question is framed. Although the question is of very simple standard, but actually officially it is not in the syllabus prescribed by IIT. Anyway, let us see the solution. In a given 8-bit general purpose microcontroller, there are following flags: C for carry flag, A for auxiliary flag, O for overflow flag, P for parity. R0 and R1 are two general purpose registers of the microcontroller. After execution of the following instruction, the decimal equivalent of binary sequence of the flag pattern CAOP will be. Okay, so let us see. So if you see the first instruction, move R0, comma plus 0x60. So what is the meaning of it? So move. So I think students who have little bit idea regarding 8085 or 8086 or 8051 controller, which you have studied in your BTech days. So move instruction is just for movement of the data to the register, right? So this is a very common sense thing. I believe all of you should have. So move R0, comma this 60. That means what is going to happen after execution of this? So after execution of this, the register R0 will contain 60. So 60, how it will be in the binary notation? 6 then 0. Okay, by default hexadecimal notations. Similarly, move R1, comma plus 0x46. So in this case, R1 will be containing 46. What is the this 46 in binary? So 46 in binary will be like this, 46. Now the next instruction is add R0, comma R1. Now in this case you have to add the content of R0 and R1. If you add it, what do you get? 000, 011, 011, 000, 000, 101, 11, sum is 0, carry is 1, and this is your 1. So this is what you are getting. Now, so let us see what is the status of these all flag bits. So C for carry. So are you getting any final carry? Is there any carry is being generated here? It's not. So definitely your carry flag is 0. What about auxiliary carry flag? Auxiliary carry flag, are you getting any carry from this bit to this bit? No. So auxiliary carry flag is 0. What about overflow flag? Is there any overflow? Yes, there is overflow, because we know when you add two numbers, okay, so if two same sign numbers are added and if the result is of opposite sign, we say overflow has happened. So here this is a positive number, this is a positive number. You are adding two positive number and you are getting a negative number. So sign bit is 1 means negative number, sign bit is 0 means positive number. Addition of two positive number is resulting in a negative number. It indicates the case of overflow. So the overflow bit flag is definitely your 1. And what about your this parity? So parity, you have to check the results. So if you check the results, so how many these things are there in the parity? If you check how many ones are there, so 1, if you check 1, 2, 3, 4, there are 4 number of ones are there. So you see this parity is defined as 0 for even and 1 for odd. Okay, if there are even number of 1 in the results, parity is 0. If there are odd number of 1 in the results, parity is 1. So if you check, there are 4 ones, which is even number of 1. So parity, this is again 0. So now they're asking what is the flag pattern CAOP. CAOP. So C we obtain it is 0. A we obtain it is how much? 0. O we obtain it is 1 and P we obtain it is 0. So CAOP 0010, this is in the binary pattern. So they're asking decimal equivalent. So decimal equivalent means it is 2 in decimal notation. So the answer is definitely 2 for this. So it's a simple problem, but you can say out of syllabus or whatever the way you feel. But if you have little bit basics you have studied in your BTech days regarding microprocessor, this question you should be definitely able to answer. So answer is 2 for this. This question is asked in GATE 2023 of electrical. This is from digital electronic subjects and from sequential circuit topic. The question is, neglecting the delays due to the logic gates in the circuit shown in the figure, the decimal equivalent of the binary sequence ABCD of initial logic states, which will not change with clock is dash. Okay. So what they are asking is, so if you see this circuit, so there are four signal points they are highlighting, A, B, C and D. Okay. So they're asking if we are clocking these circuits from this clock, okay, what is that state of A, B, C, D which will not change if clocks are being applied. So it looks like a simple counter circuit, students. So let us observe its corresponding counting table. So from there we'll get the idea. There are other way to solve this, but for a clarity, so let us go in the detailed approach. So for understanding purpose, so it is given Q bar. So this is, let's say it is Q1, this is Q1 bar. And similarly, this is, let's say, Q naught, and then it is your Q naught bar. Okay. Now, if you check the signal point, students, so the signal line A is nothing but connected with Q1 bar. Signal line B is connected with how much? A bar, because it's a NOR gate and both inputs are sorted, so it's act like inverter. So the input is A, then this output is A bar. But what is A already we got? A is nothing but your Q1 bar. So it is Q1 bar is A and again bar. So this is equivalent to Q1. In the same logic, what is C? So C, if you see, this is connected to Q naught. And D, if you check, this is XOR combination of B and C. XOR combination of B and C. So B is Q1 and C is Q naught. So it is Q1 XOR with Q naught. So these are what your ABCD in terms of Q1, Q naught. So let us make a table to obtain its corresponding counting pattern. So first column I would like to make is the present state. So present state is, let's say, Q1, Q naught. Then we have the flip-flop inputs. So flip-flop inputs are D1 and D naught. So let us say this is my D1 and this is my D naught. So D1 and D naught. If you observe this carefully, D1 is connected to Q naught. So in bracket I am writing Q naught. D naught is connected to D, and D is nothing but, if you see, we obtain it is Q1 XOR with Q naught. So Q1 XOR with Q naught. And then you have your next state, so which is, let us denote it by Q1 plus and Q naught plus. Okay. So let us write their combinations and then let us see. Zero, zero, 0, 1, 1, 0, 1, 1. D1 is Q naught. So Q naught column I am copying as it is 0, 1, 0, 1. D naught is Q1 XOR Q naught. So let us write the XOR combination of Q1, Q naught. 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 0, 1. 1 XOR 1 is 0. You know, these are the D flip-flops, and in D flip-flop, the next state equals to same as the what? The applied input. Q plus equals to D. So Q1 plus equals to D1 and Q naught plus equals to D naught. So in that logic, if you fill it up, so Q1 plus equals to D1. So D1 is 0, 1, 0, 1. Q naught plus is D naught. D naught is 0, 1, 1, and then it is 0. Now, if you observe, if I ask you to find the counting pattern, so what is the counting pattern of this one? So you see, so let us assume the initial condition is 0, 1. So from 0, 1, where it is coming to 1, 1. From 1, 1, where it is coming? So see, 0, 1 to 1, 1, 1, 1 to 1, 0, 1, 0 to 0, 1, again 0, 1 to 1, 1 like this. 0, 1 to 1, 1, and then 1, 1 to your 1, 0, and 1, 0 to again 0, 1. This is what is the counting pattern. And if the initial state is any of these three, so the counter will be cycling in these three states. But what if the initial state is 0, 0? If the initial state is 0, 0, if you observe this, the next state is again 0, 0. So if the initial state is 0, 0, next state is again 0, 0. So if the initial state is 0, 0, counter, even if you are clocking it 1000 times, always it will be in the same state 0, 0. And that is what the question is framed based on this simple observation. You should know from this counting pattern, if the present state is 0, 0, next state is again 0, 0. So now what is the consequence of it? So even if the present state is 0, 0, if I am clocking it, the next state, the state is again same 0, 0 only. In other words, this A, B, C, D, okay, these all are expressed in terms of Q1, Q naught, right? You can see A is Q1 bar, B is Q1, C is Q naught, D is Q1 XOR Q naught. So all these A, B, C, D, they are expressed in terms of Q1, Q0. So if the present state is 0, 0, if you are clocking it again, these states are not going to change. If these states are not going to change, why ABCD will change? It won't change. Very simple. So if the initial state is 0, 0, ABCD will be remaining as it is forever, irrespective of number of clock you are applying. So just we have to figure it out. Now what are the value of this ABCD? So for this, what is the Q1, Q0 value we are taking? 0, 0 we are taking, because if it is 0, 0, then only remaining same. Q1, Q0 value 0, 0. So if Q1, Q0 value 0, 0, so ABCD, what are these values? A equals to Q1 bar. So 0 complement is 1. B equals to Q1. Q1 is 0. C equals to Q0. Q0 is 0. D equals to Q1 XOR Q0. 0 XOR 0 is 0. So A is 1, B is 0, C is 0, and D is 0. So A is 1, B is 0, C is 0, D 0. If this happens, it indicates that the initial state is 0, 0. If ABCD is 1, 0, 0, it indicates the initial state is 0, 0. Q1, Q0 is 0, 0. Now you apply the clock. Again, the same cycle, 0, 0, it will be repeating. So this ABCD is not going to change. But we are supposed to find what is the decimal equivalent. So it is in binary. So the decimal equivalent, if you find it out, so this happens to be 8. So the signal point ABCD, they represent the binary number what? If the signal point ABCD, they represent the binary number 8. Sorry, binary number 1, 0, 0, or decimal number 8. So irrespective of number of clock applied, the state will be remaining same, that ABCD value will never change, because ABCD is 1, 0, 0, it means that the initial state is 0, 0, and that's always going to be looping in 0, 0 only, like this pattern. So it's a good logical question. The answer is 8 for this. This question is asked in GATE 2023 of electrical. This is from digital subjects and from data converted topic. The question is, an 8-bit ADC converts analog voltage in the range of 0 to 5 volt to corresponding digital code as per conversion characteristics shown in the figure. For Vin equals to 1.9922 volts, which of the following digital output given in hex is true? So what data given is, so we have a 8-bit ADC and the range of the input to this ADC is 0 to 5 volts. And this is how the ADC works, this curve. I'll explain what this curve is telling. So they are saying that if the input is 1.9922 volts, which is in this range, now what is the corresponding digital output in hexadecimal format? Okay, so let us see. So first of all, students, so in a ADC, resolution is given by Vmax minus Vmean divided by 2 raised to power n. Here Vmax is 5, Vmean is 0, right? Because 5 and 0, 5 minus 0 divided by 2 raised to power 8. So this is 2 raised to power 8 is how much? 2 raised to power 8 is 256. So this is coming as 5 by 256. If we evaluate this, so this answer is happening to be 0.01953 volts, or this is equivalent to 19.53 millivolts. 19.53 millivolts, which is close to 19.6 millivolt, let's say. It will not matter. So it is 19.6 millivolts. Okay, so 19.6 millivolt is the resolution. If you observe this curve, students, carefully, so this is the point 19.6, this is the point 39.2, it is 58.8. Now the point is, so this is the point with respect to resolution, because you see this is in millivolt units. So our resolution is 19.6, so this is resolution. So when the input is 19.6, the output is 0.1. That means when the input is 1 into R, you get it is 0.1. 39.2 is, it is 2 into R. 58.8 is 3 into R, 4 into R, and so on and so forth. So these dotted lines are always given in the integer multiple of the resolution, like 1R, 2R, 3R, 4R, like that. So in this range, okay, the output is 0.1. In this range, the output is 2. But what is this range? The range, if you see, students, so this gap is 9.8 millivolts. So that means this is also 9.8 and this is also 9.8. So this half is bifurcated into two parts, you can think of. So this gap is 9.8 and this gap is 9.8. So together, if it is 9.8, if this gap is 9.8, this is 19.6. Are you getting or not? So I can say that. So if somebody asks me, so what is this point? So this point is 1 R minus 9.8 millivolts. And what is this point? So this point is 1 R plus 9.8 millivolts. So what is the meaning of it? That means if the input voltage in this range 1 R minus 9.8 to 1 R plus 9.8, the output is 0.1. Similarly, what is the meaning of this range? The meaning of this range is if the input is in the range of 2R minus 9.8 to 2R plus 9.8, so the output is 0.2. See, this center line is 2R, but this is the entire range. This is not 2 only at this point. This is 2 at this entire range. So my point is, what is that lower range? What is that upper range? So this lower range is 2R, I mean this is 2R minus 9.8. So this will be 2R plus 9.8. Similarly, if I ask you what about this? So here this is 4R. So I mean to say that this is the point corresponds to 4R minus 9.8 millivolts. This is the point corresponds to 4R plus 9.8 millivolts. The meaning is whenever the input voltage in this range, the output is corresponds to 0.4 and so on and so forth. Okay. So this point let us keep in mind. So now coming to this input voltage, what is my input voltage? So the input voltage is 1.9922 volts. So if you write this in the millivolt units, it is 1992.2 millivolts, isn't it? If you write in the millivolt units. Okay, fine. Now what you do is you simply you have to now check it out. So because in a single step the resolution is what? In a single step this is 19.6. So in how many steps it will be reaching into these values? In how many steps it will be reaching in these values? So only for calculation, I mean just to get an idea, if you do this 1992.2 divided by 19.6, so this answer you are getting this as 101.64, I think. You can check it out once. If you do 1992.2 divided by 19.6, so yes, this is coming as 101.64. So let us, we got this idea about this number 101.64. Now let us see what is going to happen. So with respect to 101 and 102. So what is the meaning of 101 and 102? So if the input is V in is, suppose if the input is 101 into R. So what is R? R is 19.6. So what is 101 into 19.6? If you check it out, so this is coming as so 101 into 19.6 millivolts. So this is coming as 1976.6 millivolts. So what is the meaning of it? The meaning is when the input voltage is in the range of 1976.6 plus 9.8 millivolts to 1976.6 minus 9.8 millivolts. In this range, if the input is, then the output is corresponds to 101 in decimal, which is equivalent to 65 in hexadecimal. That is why I have explained you this logic, this range. So I got some idea. So 101 into R is coming this one. So that means this value plus or minus 9.8 millivolts for this entire range as per the waveform given. So the answer would be 101. Its decimal equivalent 101. The hexadecimal is 65. Okay, in hexadecimal notation. But what is this? What is this thing? So if you check it out, so this value is coming as 1966.8 millivolts to this is coming as 1986.4 millivolts. So that means if the input is in this range, then the output is your 65 base 16. But what is your input? Your input is this one, which is 1992.2 millivolts. So whether this input voltage is coming in this range, whether this input voltage is lying in this range, it's not. You need 1992. So here it is stopping at 1986. So 65 is of course not the answer. So many students might have marked 65. So 65 is not the answer. So let us go into the next step. That is, if I ask you, if the input is, let's say, 102 into R, so how much you get? So 102 into R, if you do, so that is 102 into 19.6 millivolts. So you get this as 1999.2 millivolts. So what is the meaning of it? If the input range is 1999.2 minus 9.8 millivolts to 1999.2 plus 9.8 millivolts, then in this case the corresponding output is 102 in decimal notation, or this is 66 in hexadecimal notation. So if you evaluate this quantity, so this is coming as 1989.4 millivolts to this is coming as 2009 millivolts. If the input is lying in this range, then the output is 66 in hexadecimal notation. Now, whether this input 1992 is lying in this range, yes, 1992 is lying in this range. So because this is lying in this range, so the corresponding output is 66 hexadecimal notation. So answer has to be 66. So the reason I'm explaining this much is, so the confusion among the student is whether the answer is 65 or 66. For that, this waveform is given, students. You should have the idea. So these center points are the integer multiple of resolutions. So the other extremes are plus or minus 9.8 millivolts. So by dividing this with the resolution, you got 101.64. So I have taken 101 into R. So with respect to that, I have calculated what is the range it is coming. So if I am taking 101 into R, the range of input voltage is coming this one. So if this could have been the voltage, the voltage would have been lying in this range, answer would have been this much. But my voltage not lying in this range. Then I am going to the next 102R. So if the input is like in this range, so by taking 102R and by doing minus plus 9.8 volts, we got if the input is in the range of this to this, then the output is 66 hexadecimal, and of course the input is lying in this range. So answer has to be 66 hexadecimal. So answer is option C for this, right?